So I used to think the primary function of enemies in games was to present a challenge to be overcome by the player. But when I think of my favorite games like Resident Evil, XCOM 2, the Batman Arkham series, Sifu, Tunic, Mirror's Edge, it's clear that that's not always true. Sometimes enemies present a challenge, but they almost always create interesting scenarios for the player to be in. And goal-oriented action planning is a great way to create interesting scenarios. What's good, everyone? I go by Shinobi, and this channel exists to show what I'm learning and get feedback from you. And I've been learning a lot about GOAP lately. I'm calling it GOAP. I'm more of a acronym as words kind of guy anyways. I recently did a video about the pros and cons of GOAP, and I seriously underestimated how many people wanted to see how I implemented it in UE5. So that's what this video is about. I'm going to explain my implementation of GOAP, starting from a high level or like surface kind of deal, then digging into blueprints using this zombie game that I'm working on. But first, you should know a few things. This isn't a full-blown tutorial, so I won't always be going node by node explaining each one in this video. There are a few parts where I will do that, but not all the time. Also, this implementation is still a work in progress. It's not all implemented and it isn't perfect. I'll point out the flaws and changes that I'm making to address those as we go. So let's start with ideation. Since I wanted to use GOAP to create interesting scenarios, I started by thinking up some interesting scenarios involving zombies. They could see you and chase you, they can hear a sound and come investigate. Creating hordes, accidentally or intentionally, would be cool. Changing behavior based on hunger. Occasionally having the zombies fight for resources, and having a normal routine when they're not actually hunting. This is something a few of you suggested in the pros and cons of GOAP video, but it was also done in one of my favorite manga, I Am a Hero. So I figured a zombie that can do all these things would be pretty smart. Maybe even smart enough to enroll with the sponsor of this video, Southern New Hampshire University. So I definitely can recall a time when I felt stuck at a job I didn't like. For me, it was my first job out of college, and I wasted 7 years there, really just making a bunch of excuses to not quit and find work that would be more fulfilling for me. But the beautiful thing about my computer science degree was that it offered a ton of flexibility and gave me the freedom to pursue a new job, as well as dive into game development here. And that's what I love about the game development degree program today's sponsor, Southern New Hampshire University, provides. SNHU offers multiple fully accredited degrees in game development, one tailored towards game art, and the other towards game programming. SNHU makes your success their mission, so they offer these courses online with multiple start dates to be as flexible as possible. Since they're online, you can attend class whenever and wherever it's convenient for you. They also offer loads of other resources like academic advisors and career services as you need them. Now, from my personal experience, I know how difficult it can be to find reliable information while learning game development on YouTube, but SNHU hires staff with real-world experience, so their specially trained instructors are capable of helping you develop the skills you'll need for success. I'm gonna be honest with you here. The real reason why I'm rocking with SNHU now is because they offer solutions to problems anyone considering higher education is facing now. The first of which is student loan debt. We all know how wild it is, especially if you're in my generation, but SNHU prioritizes affordability for their students by having one of the lowest priced online tuition rates in the nation, so you can achieve your dreams at a price you can afford. Second is the job situation in the gaming industry. We've all seen the layoffs that have been happening, but gaming degrees that SNHU offers will help prepare you because they'll teach you skills that are valuable in multiple industries. Through their program, you can learn to code in C#, Java, and C++. They also offer classes in digital graphic design and 3D art and design. So don't be like I was. Don't spend any more time at a career you hate and start taking steps to get where you want to be by going to snhu.edu/shinobi for more information, or just hit the link in the description. All right, let's get back to it. So now that I know what I want to make, we can get into how this translates into GOAP. We already went over how GOAP works in a separate video, so here's a brief overview of how it works. It's more like a design pattern, a general solution to a problem, than a hard set of rules to follow and program to. For my implementation, there's going to be 5 parts of the system. I followed Justin Young's article on GOAP closely. It's linked below. So the first part of the system is the agents. These are the NPCs in the game, and they're dumb, so they need someone to give them some direction. And that direction is going to come from the planner. The planner is going to be our responsible adult. It uses an algorithm to generate a plan for the agent. But in order to generate that algorithm, the planner needs to know a few important things. The first of which is going to be state data. State data is data about the environment. It's usually stored in key value pairs just because it's really easy to read and manipulate data that's stored like that. And this is going to be things like resources that are available to it, tools, objects in the world that it can interact with. The planner also needs to know what goals the NPC has. And these goals, at least in my implementation, these goals are based off of the world state data. Basically, the NPC is going to look at the world state data and try to figure out what that world state data should be. So, for example, if the NPC knows the player is alive, then its goal will be to go and kill the player. And so what that looks like in terms of state data, if the world state data has a boolean in it called is player alive, and that's currently true, its goal would be to set that to false. And the last thing the planner needs to know is actions that are available to the NPC. Actions are going to be units of activity that lead to a goal being met. I implemented a cost component because it allows me to take into account which actions should take a higher priority over other actions. And I think the important, well, at least the most interesting thing about actions is they come with a set of preconditions and a set of effects. The preconditions in my use case are world state data that needs to be true for this action to happen, and the effect is how that world state data changes after the action happens. So when you put it all together, this is the system that you get. You have the NPCs requesting plans from the planner, and the planner takes into account the state data, the goals, and the actions that the NPC has, and sends a plan back to the agent. Depending on how you choose to implement your system, state data, goals, and actions can be stored in a number of different ways. For mine, the state data, actions, and goals will be stored within the agent itself. And since the planner is going to have access to that information when it needs it. So that's the system in a nutshell, but what do these components actually look like? We can go one level deeper. I like to start off with paper, so here's how I broke down the GOAP system for this project. So here's how I broke this system down on paper, starting with state data. I looked at this data as the data observed by the NPC. It's used to drive decisions for the actions that it will take. Some of this is redundant. I'm planning on cleaning that up later, but I think you can get the gist of it from this. I wanted this data to be represented in key value pairs, and so here's what I have. First of all, we have a player reference. This is just a reference to the player that only gets set when the NPC sees the player. It's on a timer, so it's on set if line of sight is broken. It's used to trigger chases and attacks right now. Last known location gets set on an interval when the player reference is set. This allows the NPC to keep chasing the player after losing the line of sight and then search the area that it last saw the player. Is player alive is pretty obvious. This ties into when death animations play, and eating the player. Has line of sight is redundant, but it's also used for chasing. Market locations is areas to scout for food when the zombies are hungry, so they can go back to normal routines without hunting the entire time. It's really just a workaround for not having waypoints. Other zombie allows the plan to account for following zombies, is following zombies, accounts for if that zombie has food and can trigger eating sequences, as well as signals to other zombies that they may want to fight you. Is full will trigger the normal routine. Area search is not being used right now, and flee is just a way to end fights that happen between zombies. I know there was a lot, but hopefully it'll make sense a little bit later. Next, I have the goal states. Since there's multiple goals that need to be organized in some sort of priority, right? These goal states are what we're trying to make the world state data match, right? So our first priority is always going to be to try and kill the player. So it wants is player alive to be false. And if it doesn't have a player reference set, then it wants has food to be true. So it's gonna go create a plan that ends with it finding food. And the third priority is just gonna be eating the food, right? So it wants is full to be true so it can go back to its normal idle routine. So this is where things start to get a little more interesting. Actions. Actions have a precondition, something that must be true for that action to happen, the action itself, and an effect, or the results from that action. State data defines the preconditions, and the action mutates the state data when it produces an effect. The actions I've chosen to have are eating, chasing a player, searching an area, following a zombie, fighting a zombie, going to a market location, idle, flee, and wait. Let's look at search area as a decent example. Search area has two preconditions. Either one of them can be true. We're either chasing the player but we lost track of them, or we went to a market location and we want to search for food. And the result of searching an area is we either find the player again, we find food, or we find nothing. So based on the NPC's current state, if the right preconditions are met, it can decide if searching the area is the best way for it to reach a goal state, or if it should do something else. And once the act of searching the area has happened, based off of the effects and the way that those mutate the state data, it will either be able to change the plan and do something else. So in my implementation, since the goal state are the desired mutations of world state data, I think you can see how like the planner might decide searching the area is the best course of action to get to a state where the player isn't alive, or get to a state where the NPC has food to eat. So we've got all the components drawn out, but we still need a network graph. So here's what I came up with. The point of the network graph is to show how these nodes connect. In our case, the nodes are actions. And there are many different types of network graphs, but I'm using a weighted directed graph. Weighted means some connections or edges are more expensive than others. This is used to influence the paths that are chosen. In my graph, the weight is represented by the number attached to the edge. Directed means not all edges can be traversed from any vertex. In my graph, edges that have an arrow going both ways means it can be traveled in either direction. But some are one-way edges. So for example, we can go from following a zombie to chasing a player, but we cannot go from chasing a player to following a zombie. There are a few issues with this system as it stands right now. The main one being, I think this should have been split into 3 graphs. When I revise this, I'll probably call this one hunting, and then move chase player into its own graph to allow for more complex behavior. And I'll also probably move idle into its own graph since there's some unique activities that are going on well. And I think this would translate into hitting those nodes, changing the state tree, and the planner being used. Just to explain this graph a little bit more, let's just take an example. So let's just say we're at weight, right? When we pass this information into the planner can say, okay, we're at weight. Our options are to go to the market, to search an area, to fight a zombie, follow a zombie, or to chase the player, right? And so if the objective is to get to this eating phase, right, the algorithm will be able to say, okay, if we go market, search area, eating, that's going to cost us 3. But if we go to chase player, eating, that only cost us 2. If we were to go to follow zombie, then chase player, then eating, that would cost 4, right? So that would be a more expensive option. And the planner will be able to take into account the cost of each path, the cost of each option, and try to determine something that gets to the goal state, but also takes into account some seemingly random decision making. So now that I've defined what I'm making, I can start to translate the stuff into blueprints. I wanted to make the system modular and scalable, so I decided to implement it using an actor component, and state trees. It's not implemented exactly like this yet, but once it's in its final form, the idea is to have all character specific things contained in the actor. So like the adjacency matrix, state data, goals, a current plan array, and a current action integer. And the actor component will contain all GOAP specific things like the planner and its algorithm, because it'll be modular and I can just hand that logic to whatever actor needs it. And the state tree is just what I'm most comfortable using to facilitate transitions between states. I like that they have conditions baked into the structure so I can leverage them as preconditions, but you can do that part however you want. You can do all of this however you want. So I'll start with the network graph. Remember this weighted graph? Well, graphs in code are represented as adjacency matrices. And adjacency matrices are 2D arrays, or just arrays of arrays, or just an array of arrays. So here's what that would look like on paper. Each row represents a node in our graph, and each column represents a connection to another node. A 0 in a cell means there's no connection to that node, and any other number represents the weight of that connection to that node. So we can look at, let's look at a node as an example, right? I believe chase player is number 2. So you can see chase player is number 2. And if we look at 0 has 0 in it, so there's no connection to node 0, but 1 has a 1 in it, so there's a connection to node 1. So if we go back to our network graph, 0 is going to be flee. So there's no connection directly from chase player to flee, but there is a connection from chase player to eating, because eating is 1, and that's how that's represented in this 2D array. Now there is one small problem with 2D arrays in Unreal Engine, and that's Unreal Engine does not support 2D arrays. So I had to come up with a workaround. I decided to go with a struct of arrays, and currently this struct lives in the actor component, but I'll be moving it to the character soon. Here's what that looks like. So each array is named after one of the action nodes, and their numbered order matches what's in the chart itself. And now if we open up the structure and we take a look at the default values are going to match what's in the 2D array, right? So let's look at chase player again. Index 0 has no connection to 0, but index 1 has a connection to 1 with a value of 1. And I think this worked pretty well after I figured out how to access this thing. And next we can take a look at our world state data. So this is a struct of values in the character. As you can see, there's a number of different ways that the data is represented. The player reference is a reference to the player character itself. Locations are vectors or arrays of vectors. There's booleans, there's integers. It's really easy to manipulate this data and get it to represent what you want it to. And currently, this is updated in a few ways. If we open up the NPC character, one of the main ways that this world state data is updated is through the enemy NPCs AI perception component. So all that's happening here is when we sense something, first we check and see if it's the third person character. If it is, we update the world state data accordingly. One of the things I might have forgotten to mention is you also need a way to have your NPCs change their mind. And this is how I'm doing that. If it's in the middle of a plan and it sees the player, it needs to be able to abort that plan and just go straight into chasing the player. So when it perceives the player, it stops what it's doing and sends a special event to the state tree to transition into that chase player event. If the thing it sensed was not the player character, then it checks to see if the thing it sensed was another zombie. And if it's not already like following another zombie, it'll make note that it can sense the zombie. And when the time comes for a new plan to be created, if that reference is still set, maybe the planner decides that it should just start following the zombie or even fight the zombie. And the last thing it checks is if the thing that it perceived was food. And if it is food, of course, it'll try to eat the food. Like I said earlier, I'll be trimming a lot of this data down because there's other ways to get the information that I need. For example, if I have the player reference, I can get the last known location from it when I need it instead of updating it here, which like updating it here is arguably much less useful because I'm not doing anything with it here yet. A lot of this still isn't implemented yet, but the plan is to have the world state data be updated as a part of an action or at the end of an action when relevant. So now let's look at the state tree. This is what I'm using to define what each action actually is. So for example, if we look at search area, the state tree has a leaf node called search area that has a task called search area, right? And the search area task contains the logic for that action. If we were to open it up, you'd see that right now it just selects 3 random locations in that area and moves to them. But eventually I'll give it the ability to identify hiding spots and search those hiding spots. The state tree is handy because it also comes with these interconditions, which I'll get into more a little bit later, but they allow me to control the state flow in a way that already feels similar because our actions have preconditions. So here's how it works from the beginning. At the beginning of each pass, we hit this update plan node, this update plan task, and the first thing it's going to do is check if the current plan array in the actor is empty. If it is, that means we need to request a plan from the planner. So it calls this create plan. It calls this create plan function that requests a plan from the planner. The planner returns the plan as an array of integers. Those integers align with the numbering of the node of the action nodes in our graph. And then it'll set the actor's current action to the integer at index 0 of the current plan, and it'll remove that index. And after it finishes, it pops back out to the state tree, and then it's going to waterfall down each of these actions, looking at it's going to waterfall down each of these branches, checking to see if the interconditions match the current action stored in the actor, right? So since search area is 3, if the NPC's current action is 3, it'll enter the search area node. If it's not, it'll just go on and check the next one. Now this works well for me because if a plan doesn't work out, it's pretty quick to just cycle through this whole thing until the current plan array is empty, and then request a new plan and just keep waterfalling through like that. I don't have to account for a whole bunch of like mind changes, or what happens if the expected world state settings don't match what's needed to enter the next action's preconditions. Well, it's just gonna keep requesting a new node from the current plan and then eventually request a new plan. So it handles that for me pretty easily. You might have noticed that the interconditions right now don't actually account for preconditions that are in the action, and I need to add that. I just haven't had the time to add that yet. Right now it's just checking if the current actions number matches the number for this node, and it should be pretty simple to check the world state data and add those additional checks in the interconditions here. So the last part of this system is the planner. I decided to make the planner an actor component because, like I said, I can just assign an actor component to an actor and give that actor its functionality without having to duplicate any work. Like I already said, I need to reduce its functionality to just returning a plan because currently it selects a goal, but I think in this specific setup, that should probably live in the character, since the goal for each different type of character may be different and they may have different priorities to help vary their behavior. But here's how it works. Remember back in our update plan node, when we hit this create plan function, it takes us to the actor component, and the first thing that's going to happen is it's going to select a goal. So in this get goal function, it looks at the world state data. First thing it says is, hey, is the player alive and do you have line of sight? If those two things are true, your goal should be to get to node number 2, which is chasing the player. This is another one of those redundant things because I don't think this path will ever actually be hit with the way things are set up, but that's just the way it is right now. The next thing it does is say, hey, can you see another zombie? And if it can see another zombie, there's a 30% chance that it'll either decide to follow the zombie, fight the zombie, or just keep doing its own thing. But if that is false, it either decides to go to a market location or just search the area that it's already in. That's done randomly with this find integer in range. And so after it's selected the goal, it's gonna pass that goal node to Dijkstra, right? And so this is a bit of a misnomer, but Dijkstra is a search algorithm used to find the shortest path between 2 nodes in a graph. I found that when I only found the shortest path, it wouldn't pick other routes as often as I wanted it to. So I'm not exactly doing Dijkstra anymore. It's basically Dijkstra with a couple of line changes to it, but let's dive in. So it's important to note right now our starting node defaults to 8 because usually when we're requesting a plan, we're in the waiting state. That's just not something I've implemented yet. When we click into Dijkstra, so when we come into Dijkstra, the first thing we do is some housekeeping. We got to set up some stuff and initialize some things. Our starting node is going to be the node that we start at, and the end node is going to be our goal node. The number of nodes, there's no reason to set this dynamically that I did. You can just set it to the number of nodes that you have in your graph. And the first thing we're going to do is initialize this distances array. This tells us which nodes are accessible at what cost from our current node. We set that all to -1 to begin with. And then we also initialize this predecessors array to -1 as well. Predecessors is going to be what we're going to use to build the path after we found the goal. You need this to keep track of the path that you take to get to the goal. So after we initialize all those things, first thing we do is come into our distance array and set the distance of the starting node to 0. That just represents the node that we're starting at. and we hit our first loop, we're gonna set a minimum distance variable to -1 and the current node to -1. And then we hit our first nested loop. This nested loop is responsible for finding the next current node. If no next node is found, all paths have been explored and the algorithm is completed. So all this for loop is doing is running a conditional that checks and sees if this visited array, forgot to mention the visited array. This visited array is a Boolean array. Every entry is set to false, and this is how we keep track of whether a node in the graph has been visited or not. So for each index, for each node, we check and see if that has not been visited and if the distance is greater than -1. Because if the distance is greater than -1, that means there's a path there that can be traversed. So if we haven't visited this node and its distance has been set, we set the minimum distance and we set that node as the current node. And after that for loop is completed, we check and see if current node is still -1, that means we never found a new node and we're finished. Or if current node is equal to our end node, that means we found our goal and we're also finished. If both of those things evaluate to false, the first thing we're going to do is set the index of our current node in our visited array as visited. And then we're going to fall into our second nested loop. The second nested loop is responsible for calculating the distances of all unvisited nodes, of all unvisited adjacent nodes next to our current node. So in order to do that, we just gotta access the array for our current node that's in our adjacency matrix, and we check and see if the value at the index within the array does not equal 0. Because if it does not equal 0, that means there's an edge there that can be traveled. And if that edge connects to a node that has not been visited, that means there's a path and we need to make note of it. So how we make note of it is we set this alt distance value, letting us know that there's a way to get to this node that only costs this alternate distance. Now, if we were doing normal Dijkstra, we would check and see if the minimum distance if the alternate distance is less than the minimum distance, then that minimum distance would become the path that we want to take. But because I wanted a little more variation, a little more randomness, I decided to make it a 50-50 chance whether we take that path or not. And if we decide not to take the path, we just keep track of like the fact that a path exists there. And if we keep going through this and we don't find any other paths, we can fall back on this potential node and use that instead. So after all that is done, we go back to our distance array and we update the values within that array to reflect like what distances we can take, and we also update the predecessors to keep track of the node that we've currently decided to add to our path. After that's completed, we come back to our initial loop and we go down the completed path, which means the algorithm is now done and all we got to do is return a path, right? And so the first thing we have to do is construct the path from predecessors, and that's done in this get path function. So within get path, what we're doing is we're building the path, or rather the plan, that the NPC will implement from end to beginning. So the first thing we do is we set our end vertex as the current node, and our start vertex is what we're going to compare to see if we've finished constructing the plan yet. And the first thing we're going to do is we're going to enter into this while loop that's based on a conditional. If you're going to do something like this, just make sure that the condition that makes the loop false will happen somewhere within the loop. If you mess it up, it's not a big deal. You just end up with infinite loops, and yeah. But anyways, the first thing we do is we have this path array. I should have called it this plan because it's the plan that we're building, and we're going to return it to our update plan node, and it's the update plan node is going to set this as the plan after it's done being constructed. So we take our current node, we add it as we add it to the beginning of the path array, and then we get the index of current node from predecessors, and we add that and we set that as current node. And then all we're going to do is we're going to check and see if current node is equal to our start vertex, which is where we're at now. If it's not, we loop through this again until we've gotten all the nodes that we need to build this plan. But if it is, we're done, and all we got to do is add this last node to our plan and terminate the loop, and then we're just going to return the path. And the path gets returned as the plan, and the plan gets returned and set as the NPC's current plan. And that's it. That's how this thing works. I know it's confusing. I wouldn't say it's confusing. It's just, I know it's a lot to take in, but yeah, that's how this whole thing works. So that's it. That's how my GOAP implementation looks currently. If you found this video helpful, please hit the like button. And if you got any feedback, negative, positive, or whatever, please just leave a comment. I sincerely appreciate it, and I just want to give a big thank you to all those who asked for this video and have waited the month that it took for me to make this video. You know, between my wife, my baby, and my 9 to 5, it's just hard to find the time to record this stuff, let alone even like program and figure this stuff out. I appreciate y'all. Peace.